Hi, welcome to the lecture on adaptation of animals. Now we will check more on the muscle contraction, but now on the macroscopic level, so the whole muscle level. If we put the movement as simple as possible, we have bones in our body and we have muscles, and these skeletal muscles are binded on these bones. And these skeletal muscles, there exists muscle on both sides of the bone, and they are working together as antagonist pairs. So when one muscle is getting shorter, the other one must get longer. And when the muscle is getting longer, it's fighting back against this shortening of this one muscle and moving the bone. And that's why it's limiting the speed of, for example, of this bone direction change, and also limiting the damages that could happen if all the shortening and moving the bones would happen too fast. And when you are picking particles from the floor, you are bending your knees, and then you have muscles that are contracting, like gastrocnemius muscle or soleus muscle there in the behind your leg, and you feel that okay, these muscles are a little bit hard, so they are contracting, and in the middle there's this contractile component, and that's stretch the elastic components, and this kind of contraction is called isometric contraction. So these sarcomers are shortening slightly, and they pull the elastic elements of the muscle. But because the elastic elements pulling them, they are fighting back passively. So that's caused that okay, the whole muscle is not moving at all. And this is something that is you all know that okay, when carrying heavy bags or whatever, so your hand muscles get quite fast, quite painful. It gets painful because the muscles are contracting, but they are not moving. Then we have the normal mode of contraction. We have concentric contraction, so the muscles are getting shorter. But also the lengthening of the muscle is active. So we have eccentric contraction. There are cross bridges are generating this force to limit the speed of lengthening. And that doesn't happen that, okay, you just lose these cross bridges, because otherwise, in that case, the whole muscle would stretch very fast to very long, and that most probably there would be some damages. And there's still one more contraction. We have isotonic contraction, meaning that the tension is constant, and meaning that okay, you have a certain load that this muscle is moving when it's contracting, and this load is always the same because you have, for example, some weight. And this is something that happens in the laboratory every day, but in the real life hardly ever. So these bones and muscles, they are working together, etc. So most probably the contractions are not isotonic. So what happens on the sarcomers when these muscles are working? Well, if we are in the rest, nothing happens. There are no cross bridges that are active. And if it's isometric contraction, these elastic elements are stretched because the sarcomer is getting shorter. But because the elastic elements are not stretching anything else, so for example the bones are not moving, so that's why the whole muscle stays at the same length. But the cross bridges are anyway active. Then if we have isotonic concentric contraction, so the whole muscle gets shorter. It gets shorter because these cross bridges are now active, and they are pulling these elastic elements that are pulling whatever there exists binded in the ends of the muscle. And when we are pulling the muscle in opposite directions, it first affects that, okay, these elastic elements are stretched. And this causes then that this overlap of thick and thin filaments are decreased step by step. So, and causing that slowly this whole muscle gets longer. So again, these cross bridges are active. And how these muscles are working if we are not stimulating them? They work as like a rubber band. And it's very simple the way to test. You have a hook, and then you have some kind of meter to say that, okay, how much force you need when you are stretching the muscle. And when you hook it in a mechanical force cord and stretch, the force will increase exponentially when the length of the muscle is increasing. And that's very typical if you ever have a rubber band. So if you stretch it very far much, then there is a lot of energy, meaning that there is an increasing force. And then when we have active muscle, they operate actually a little bit differently. So when doing the same thing, stretching the muscle, but now stimulating the muscle, you can measure the total force. And this active force is increased already at mild stretch. And the maximum is there somewhere between the extreme length and in the very low length. And if you are comparing them, you can measure the active force, and it has somewhere between the maximum and the minimum, and it's actually somewhere before the passive force is really rising. So the active force is every muscle has some kind of stretched situation where it can generate most energy for the contractility. And we have two different words. We have tension and force. So if we nail the muscle at both ends, then the tension is formed, but the muscle is unable to move. So that's why it's isometric recording. And we have already learned that, okay, we can have a stimulus for the muscle, and we know that, okay, where the time goes in the latent period before the calcium is there in the regulating this contraction. And then we have contraction phase that happens in a few milliseconds or whatever, and then the relaxation phase. And the same phases also happens when we have this contraction on the isotonic contraction. But now, for example, on one end it's not nailed, but there is, for example, a string which is moving together with the muscle. So that's why now, because the muscle can contract, then some time is used so these thick and thin filaments are moving across each other, and that's why this contraction phase happens a little bit slower. And it's very simple to measure this force of the muscle. It was studied actually already in the beginning of 20th century. The original idea was they tried to measure that how much heat is released when the muscles are contracting. So there's a hook on both sides of the muscle, and in one part of the one hook is attached on a pen there on the right, on the top right, and then on the other hand of other end of the pen there is a preload and afterload. So they first put small weight, this preload, to stretch the muscle, and then put the stop to limit the change of the length while adding the afterload. And then by testing with different kind of loads, they were able then to measure that, okay, how much contraction how much load this muscle can move, and how fast it can move, and how much, for example, the original idea was that, okay, how much heat it's producing. So when the muscle is contracting, now the stop is removed to see that, okay, how this contraction can use the energy to lift the load. But the original experiment was not working, because when you add different loads, there's a clear difference in the velocity. So how fast this length is changed. So how fast this contraction happens. And that means that, okay, the heat depends on the weight of the load. So if you have very high load, then you are making isometric contraction. So it can't contract at all because the load is too heavy. Then if you are putting a little bit lower load, but it's still heavy, the contraction happens. The length changes only slightly, but it also happens slowly. And if you have very light load, then the contraction is much faster and also much larger. And from there, they got that idea that, okay, there's some kind of force and velocity relation. And it showed two important relations. So first of all, the load decreased the velocity exponentially. So that's why you can lift light loads much faster. And although it's exponential, actually there are quite many equations to describe this exponential decay. So it's still a little bit under debate that, okay, what is the best equation for this? So what really happens? And then the second thing is even more important. When you are multiplying the load and velocity, so then you can get the power output of the muscle. And now you have hyperbolic relation. So that's why you have optimal contractility at certain weight for different muscles. What then happens when we have either single stimulus or multiple stimulus? So a single stimulus causes that, okay, there is a calcium release, and that causes the contraction, and then you remove the calcium and the cell will relax. And with low frequencies of this stimulus, it causes these individual switches. And so there's no summation. But then, when you are decreasing the interval between the switches, there will be the force is larger. It's a cumulative. There happens this summation of this force. And if in high frequencies, some sarcomers are now fully contracted, and this causes that, okay, the force is much higher and the line is quite steady. So it's there's not so much movement as in the previous, in the summation. So you can't see these individual twitches anymore. And when you are having extreme frequency, all these sarcomers are fully contracted. And it's very straight line, because because if they are already fully contracted, they can't contract anymore. And so this happens in the skeletal all skeletal muscles quite easily. That okay, we can have this summation, and in high frequencies also the tetanus. And you can see that now this tetanic force is much higher than in these individual twitches or even the summation before the tetanus. And in these cases, it's in a frog muscle, skeletal muscle, and it's about 10 times higher. But in the mammalian cells, typical 3 times or 4 times more in the tetanic force is quite typical. And what's the idea behind it? So when we are triggering the muscle with the electric shock, we got maybe 2 millisecond long action potential. We saw the action potential already in the previous videos. And this action potential causes that there is a release of intracellular calcium, and that you can also record. And as you can see, although it happens almost at the same time with a little bit delay, but the decay is much longer, because the calcium must be uploaded by using ATP energy in this calcium pump when they are putting the calcium back in the acer. So it's much slower process than in the action potential. And if you are having higher frequency, there is calcium that is not uploaded back to the sarcoplasmic reticulum. So that's now there is a mismatch in these calcium pathways. So you are releasing calcium in the cytosol, although there was also already some calcium. And this caused the accumulation of this cytoplasmic calcium concentration. And this caused then that, okay, there is summation and the tetanus of the contraction. And then, what about the tension in different muscles? But so far we have discussed that, okay, we have skeletal muscles, and they contract quite fast, they relax also quite fast. Then we have cardiac muscles. They are much slower. So the contraction happens quite slow, but also the relaxation happens quite slow. And if we remember in the previous videos, there was a huge difference between how long the action potential versus how long this contraction happens in skeletal muscle and cardiac muscle. So in the cardiac muscle, the action potential was half a millisecond or 100 milliseconds or whatever. So it's quite long. So that's why it's unable during this action potential to get the next stimulus. So that's why you can't make the tetanus in the cardiac cells. But these still are quite fast to compare the smooth muscles, where the contraction happens within 2 seconds or whatever. And already we learned that, okay, the whole excitation contraction coupling was completely different in the smooth muscle. So again, what happens in this tetanic in the skeletal muscle, most probably that's not happening in the smooth muscles. And still one more type of the muscle we had these fast skeletal muscles and slow skeletal muscles. And they have a little bit difference in how fast they can produce the tension, how fast they can release the tension, so the decay happens, and also there are some interesting things between them, but that's another story that we are going to have on the next video. Thank you.